Welcome to This Explainer. I am so thrilled to have you here today. Let's just dive right into it, because today we're talking about a fundamental step in data analysis that honestly gets completely overlooked in the rush to get results. Before we even think about running complex models, and before we start looking for exciting insights, we absolutely must give our data a rigorous health check. We need to look at the very shape of our data.
So here's our roadmap for today. We're going to cover the rule of assumptions, the perfect bell curve, skewness and kurtosis, how to actually diagnose your data, and finally, why normality matters so much.
Section 1. The rule of assumptions and baseline data health.
Think about a patient walking into a clinic, right? Before prescribing some advanced treatment, what does the doctor do? They check the baseline vitals, heart rate, blood pressure, temperature, the whole shebang. Well, data analysis works exactly the same way. So I've got to ask you a pretty provocative question right out of the gate. Do you actually trust your data? I mean, it's so easy to look at a massive spreadsheet full of numbers and just assume it's ready for modeling. But raw numbers can be incredibly misleading if you haven't done a proper diagnostic check. Because listen, just because you have volume doesn't mean you have health.
And that brings us to statistical assumptions. Basically, these are the baseline conditions, the ground rules, that your data absolutely must meet before you run any parametric tests, like regressions or ANOVAs. If your data fails to meet these foundational assumptions, say the assumption that your population scores are normally distributed, well, the results of your statistical tests could be completely invalid. You could end up drawing entirely wrong conclusions simply because your foundation just wasn't solid to begin with.
Section 2. The perfect bell curve, the gold standard.
Now, when we're talking about data health for continuous variables, this beautifully symmetrical normal distribution is our gold standard. The data clusters in a perfectly balanced way right around the mean, and the frequency just decreases gradually as you move outwards. This idealized shape is exactly what our parametric statistical techniques assume they're working with.
Let's break down the specific traits of this perfect bell curve, which is essentially our data's clean bill of health. First off, it has perfectly symmetrical sides. And because of that symmetry, the mean, the median, and the mode, they all sit at the exact same point, right there in the center. Also, check out the asymptotic tails. They stretch out into infinity, getting closer and closer to the baseline, but never quite touching it. And if we're speaking mathematically, a perfectly normal distribution has a skewness value of exactly 0 and a kurtosis value of exactly 3.
Okay, moving on to section 3. Skewness, leaning left or right. So skewness is the first symptom that really distorts that perfect curve. You'll notice there are two distinct ways the data can lean. With a positive or right skew, you get this big buildup of low scores. The most frequent scores cluster down at the lower end, and that tail just stretches way out, pointing towards the higher positive scores. And because of those extreme high scores dragging out the tail, the mean is actually pulled up, so it's greater than the median. On the flip side, a negative or left skew means there's a buildup of high scores. Here, the tail points to the left, toward the lower or negative scores, and that ends up pulling the mean down, so it becomes less than the median.
Visually, it's pretty striking. You can see that positive skew on the left. It's like a mountain of low scores just dragging this long tail off to the right. And then on the right side, we have the exact opposite, a negative skew pointing left. You can really see how extreme, infrequent scores literally stretch the physical shape of the data out in those directions.
Section 4. Kurtosis. Heavy or light tails.
Now, if skewness is all about leaning, kurtosis, which is our second symptom, focuses entirely on the extremities. We're talking about the tails of our distribution. Kurtosis basically tells us the degree to which scores cluster out at those ends. And we have two main types to watch out for here. The first is leptokurtic, which indicates positive kurtosis. This is a heavy-tailed distribution where you simply have way too many scores lingering out in the tails. The second type is platykurtic, or negative kurtosis. This one is a light-tailed distribution, meaning there are actually too few scores in the tails compared to that perfect, healthy, normal distribution.
Just take a look at these histograms. The leptokurtic shape on the left spikes incredibly sharply in the middle, and that pushes a heavy load of data out into those thick tails. Honestly, it almost looks pinched, right? Meanwhile, the platykurtic shape on the right looks entirely squashed or flattened out, with these very light, thin tails. It goes without saying, neither of these represents the smooth, symmetrical bell curve that our statistical models are expecting.
All right, Section 5. Diagnosing your data by testing for normality.
So how do we actually run the lab tests to diagnose these deformities? Well, we have a couple of dedicated normality tests at our disposal. For small sample sizes, typically we're talking under 50, we use the Shapiro-Wilk test. For larger sample sizes, we turn to the Kolmogorov-Smirnov test. But here is the absolute crucial point. and it's all about how we interpret the p-value. In most research, we usually want a p-value under 0.05 to show a significant finding, right? Well, for normality tests, it's actually the exact opposite. A p-value less than or equal to 0.05 is a totally bad thing for normality. It tells us that our data significantly deviates from a normal distribution. To pass this health check, we actually want a non-significant result, where p is greater than 0.05. And that's because our null hypothesis here is that the distribution is normal. Besides those formal tests, we can also mathematically check our skewness and kurtosis values by converting them to z-scores. The steps are actually pretty straightforward. First, you just take your skewness or kurtosis value straight from your descriptive statistics. Second, divide it by its standard error. Third, just ignore any minus sign. We only care about the absolute value here. And finally, if that resulting score is greater than 1.96, your deviation from normality is mathematically significant. Although, actually scratch that. A quick word of caution here. If you happen to have a very large sample size, you should probably avoid this specific significance test altogether. With massive data sets, even tiny, completely meaningless deviations from normality are going to flag as significant, which isn't super helpful.
Of course, math should always be paired with visual tests. Here's what real-world diagnostic plots actually look like in software. On the left, we've got a histogram that is visibly skewed. It definitely does not look like our perfect bell curve. And on the right, we have a detrended normal QQ plot. Now, for a perfectly normal distribution, those data points should fall roughly along that flat, solid zero line. But as you can see here, these dots are bouncing all over the place. It's clearly violating the assumption of normality.
Section 6. Why normality matters. The big picture.
We've looked at the diagnostic tools, but let's take a step back and tie this all to the big picture. The reality is simply this. You cannot build a robust, generalizable model if the foundation of your statistical assumptions is broken. If you rely on parametric techniques, they inherently assume that the populations or samples are taken from are normally distributed. If you just ignore the shape of your data, you are literally compromising the integrity of every single p-value, every correlation, and every finding that follows. At the end of the day, a sick data set will only give you sick, completely unreliable conclusions.
So, as we wrap up this explainer, I want to leave you with one final thought to keep in mind the very next time you open up a data set. Before you eagerly hit run on your next advanced model, ask yourself, have you checked its shape? Have you done those vital diagnostic checks? Thank you so much for joining me today, and I really challenge you to apply this exact framework to your own data. See you next time.